so we see the evolution here from what we started with on the circuit redraw. We consolidated these series resistances and consolidated these series resistances right here and here, REQ1 and REQ2. And then we consolidated using the product over sum rule these two resistances and these two resistances. And now we get REQ3 and REQ4 both in series with R1. At this point in time, can we find a total resistance? Okay, what would the total resistance be?
6.61.
Okay. RT equals 6.61 ohms. We could also find the total current at this point. This is 15 volts here. Same here. We could also find right now the total current, which would be take the 15 volt source and divide it by 6.61 k ohms. 2.27 milliamps for our total current. Which direction is current flowing here? Counterclockwise. So at this point, we could take the current around the loop and follow the voltage drops for each of these areas. 2.27 milliamps across the 3.61 k ohm equivalent resistance would give me what for my REQ3?
8.19.
What's that?
8.19 volts.
8.19 volts. Okay, how about for the REQ4? 2.27 milliamps across the 2 k ohm resistor.
4.54.
4.54 volts. And the REQ1, or rather VR1, not REQ1, just VR1. What's that going to be? 2.27 volts, right? We can just do that. Coefficient times 1, keeps it simple. Well, we've got our voltage drop for R1 now, but can we get the voltage drops for these parallel resistances? Okay. For one, I know I can also apply the current divider rule, right? For these two parallel ones. Yes, I can apply the current divider rule by taking the total current and multiplying it times the resistor that I'm not looking for. In other words, if I want to find the current for R5, I would take REQ1, okay, divided by R5 plus REQ1 and multiply that times our total current. We won't do that here because it complicates things from what we're working at right now. Instead, we'll take the voltage drop across this, and we can find the current on each leg because voltage is common in parallel. So my voltage drop here is 8.19 volts. If it's 8.19 volts in this parallel, then it's 8.19 across R5 and across REQ1. What can I say my current is for these then? Current across R5?
1.62 milliamps.
1.62 milliamps. Because we took 8.19 volts, divided it by 5 k ohms. Now I do know my total current, 2.27 milliamps, is going into this node. If 1.62 of the milliamps is going here, then the rest has to be going across REQ1. So you could perform that subtraction exercise, or again, you could divide the voltage across this branch by the resistance, in which case we get what for this leg? 630 microamps. Okay, well this is in series here as well, right? We found that voltage drop is 4.54 volts. 4.54 volts from node to node. So I could find the current across each of these branches just the same, yes? So the current across R3 would be what? 4.54 volts divided by 3K. What do we get? What's that? 1.51 milliamps, and then that would leave me with the current on the other leg to be what?
756.66 milliamps.
Microamps, you mean? Okay, and of course, we already know that the series current across R1 is 2.27 milliamps. Any questions about that? Now, at this point, we can take these currents across these REQ1 and REQ2 and apply them back into the original circuit and get the voltage drops for these resistors here. So we'll start at the bottom one here. We had 630 microamps. And from there, we could find the voltage drop of R6. Multiply 6K times 630 microamps. What do you get?
3.78.
So for VR6, we get 3.78 volts. Now, of course, we could use the voltage divider rule, or we could simply say that voltage in series is additive and get this total voltage for that branch, which we know to be 8.19 volts, and subtract the voltage from R6, and what remains will be our voltage from R7. Or we could take the current across the resistance again. But VR7 is what? 4.39 volts. Any questions about that? Now here again, we can apply our series current across this REQ, 756.66 microamps, to get the voltage drops of R2 and R4. .66 microamps across 4K ohms for VR4 leaves us with what?
3.03 volts.
Okay, and that leaves us with a voltage drop for R2 of
1.51 volts.
And now we've solved all of the circuit parameters, some of which are back in these stages. But we have solved for them. Any questions about doing the equivalent circuit method?